Hi again, and welcome to this third episode of the Einstein Telescope Industry Webinar series. Since the last episode, a lot of stuff has happened. We launched multiple exciting new projects, bringing together 7 universities and more than 14 industry partners. Together, they are tackling problems around data analysis, computing, and laser cleaning. For this third edition, we have a special episode, brought to you by our partners from NMWP, talking about the business and innovation opportunities for the Einstein Telescope. We'll kick things off with Professor Dr. Achim Stahl, who will introduce the key challenges of the Einstein Telescope. Then, Dr. Matthias Grosch and Svea Binder will dive into the opportunities within the co-making Einstein Telescope program, or COMET. After that, Ralf Meyer from Agit will present the STIPP program, and Dan Vlekke will share how his company, Netalux, got involved in the STIPP program reset. I hope you enjoyed this episode, and I'll see you back in 2 months, in May 2026.
Okay. Yeah, so let me first briefly introduce myself. I'm a physicist, not an engineer. So my background is actually astrophysics, and I wanted to give you a little bit of an overview of what the project is about. So I thought I'll give you a 5-minute introduction on the astrophysics. Then we talk a little bit about the technologies that are needed. There are many technologies, so I have to select a few. And looking at the other talks that are coming, maybe I try to cut down a bit on the time. But let's get started. So the Einstein Telescope, that's what it is about. It's a project, a European project to detect gravitational waves that come to us from space. And one of the potential sites where the project might be built is here in the 3-country region between Belgium, Netherlands, and Germany. And as from the conditional that I'm using, you see it's not approved yet. I think we're close to approval, but it's not done yet. But let me start to give you an example of what this is about. In a very clear, dark night, if you go out and you look up into the sky, this is what you're going to see. It's actually an image that has been taken in Germany, so there are clear nights like that. And what you see is a bright band that crosses the sky. And this bright band is our galaxy, the Milky Way. If I would now take a telescope, so the first one was just a camera image. If I now take a telescope and zoom into the Milky Way, then this is what you're going to see. You can see that the bright band is just an incredibly large number of stars and stars and stars. We're zooming in towards the center of our galaxy, which means this is no longer from Germany. The center of the galaxy is not visible from Germany. This is now a zoom from the southern hemisphere of the Earth. And the further in we zoom, we just see there's more and more and more and more stars coming. And towards the center, there is also a lot of what we call dust. So this is gas and small debris, which are hard to look through. And that's why we, in the last step, switched to infrared images, which are a bit better for dust. And this is what you see in the end. Then now you cannot zoom in much further because of all this dust. But what you can do is you can pick out a single star and image the star for a longer time. And what you will realize is that the star is not at rest. And this is now an image or a video that has been taken over 10, 15 years. What you see here in the upper left corner, you can see it with the blue color, is the year in which we are. So from 1992 into the 2000s, we see positions of the stars as they move around in the center of the universe. And you can see that they're circling some blue cross here, which is not an object that we can see. This is just added by the scientists. They're circling about something that is keeping them on an orbit. And from the speed, some of these stars are as fast as 10% of the speed of light. You can calculate how big the force has to be that keeps those stars on an orbit. So these are not planets, these are real big stars. And you can calculate that the object that is sitting here has to have a mass of about 100 million solar masses, and it's not visible, which means it's a black hole. So what we see there is a gigantic black hole in the center of our galaxy. This was this observation was awarded with a Nobel Prize in 2020. By today, we can actually take images, radio images of the black hole. This is now radio light in the center of the galaxy, and what we see is the gas around this black hole, which is heat up and therefore is glowing, while you can, with the resolution that's available, just see that it becomes dark towards the center. So what we see here is not the black hole itself. We see the gas that's falling into the black hole. And one of the things we would like to do is with gravitational waves is to understand where how these black holes have been formed, what their origin is, and what their function is. And we can do that with gravitational waves, which are produced if heavy objects move around. If these are what you saw there in this animation, were two black holes that were circling each other. And when they do so, they create distortions in space. That means they compress the space around themselves. And if these objects are not statically, not at rest, but if they're moving, then we create gravitational waves, that is compressions and elongations, periodic compression and elongation of space-time. And these gravitational waves can move for hundreds of millions of years through the universe without essentially any interaction with the matter or anything. And at some point, they might, oops, where did the Earth go? Okay, at some point, they might reach the Earth. And when they reach Earth, then Earth will wobble a little bit. That means the Earth is compressed in one direction and elongated in the other direction, and then the directions change. Now it's compressed in the other dimension. Obviously, the effect is a little bit exaggerated to make it visible here. It's much smaller than that. And if now on Earth, we put a precise ruler in the form of a Michelson interferometer, then this ruler will also be stretched and compressed. So I come to how the Michelson interferometer works in a second, but essentially what it does, it compares. Can you see my mouse? I hope you can see it. It compares the length between what is called the beam splitter in the center and the mirror on the right to the length from the beam splitter to the mirror on the top. And if the Michelson interferometer wobbles, then this ratio changes, and this ratio then creates light at the output, and we can measure it. I've put this here because I wanted to give you the numbers. Oh, I'm sorry, something went wrong with the font here. This should be in micrometers on the right instead of this little rectangle. This is the sensitivity that has been achieved by the current detectors. Now, this number will not tell you anything. You see it's a lot of zeros. So for reference, I give you all the mu's are gone. The wavelength of the laser, which is 1 micrometer, and this is the size of an atom if it's expressed in micrometers, and the size of a nucleus, and then finally the size of a proton, one of the nucleons. And you can see that there's still less zeros here than in the sensitivity. That means if one of these mirrors moves by less than the diameter of a proton, then we can actually detect it. And this is the basis for the technology, or not the basis, this is the challenge for the technology. What this implies is that we have to develop technologies which are capable of measuring such a tiny little change in distance. And this is what it's about. Here you see this explanation of how it technically works with a Michelson interferometer. We have a laser beam that is split here at the beam splitter into two beams. We now locate it in the wave picture. You see a wave being split into two directions. It travels out to the end mirror. It's reflected from the mirror, travels back to the beam splitter. And at the beam splitter, it meets its partner again, its other half, and we adjust the length of the arms in such a way that now valley falls into a hill of the other beam, so that we see destructive interference. And now you can see if the length of the arms changes, then the destructive interference is no longer perfect, and we do see light at the output, light that changes in intensity with the frequency of the gravitational wave that's coming in. And the big challenge is not so much to detect this light. It's actually quite some light. It's not that difficult to detect the light. But the challenge is to keep everything quiet so that nothing moves for other reasons than just for the gravitational wave. And this is an example of one of the current detectors. This is the Virgo detector in Italy. You see here at the bottom, you see this housing here. In this house, you will find the laser and also the photosensor that detects the light at the output. And you can see the two arms going on in bluish color. This is not really the laser beam. What you see is a shed over the beam pipe. So in this shed is then a vacuum pipe through which the laser is traveling, and then there's a mirror on the end towards the Apennine Mountains, which you see in the background, and the other end mirror is just outside the picture. You see the Apennine. Behind the Apennine is Florence, and you see little villages in front of the Apennine. If you follow them to the left, about 10 kilometers away from the Virgo detector is the city of Pisa, and the Mediterranean is about 5 kilometers in the back of the image. Now the question is, what happens if, for example, we have now a mirror at the end of the arm, and what happens if now, for example, a truck comes along and shakes the ground, and with the shaking, also the mirror will shake. And this is one example that I thought I will tell you about the technology. What is going to happen? Now we did not bolt the mirror to the walls. What we do is we hang it from the ceiling, or to be more precise, to hang it from a scaffolding that is bolted to the floor on a string. So this red sphere here represents the mirror. And now if the ground shakes, it means that the support point of the mirror also changes. And if the frequency is very low, in the horizontal axis, you have a frequency axis. If the frequency is very low, the mirror will just follow the motion of the ground around it, 1-to-1. And we express this by this transmissibility, and it's 10-to-0 or 1 in this low frequency region, which means the mirror moves exactly as much as the environment moves. So that's not helpful. If you now go higher in frequency, then there is this region of the resonance where it's even worse. Now we have a situation where the ground just shakes a little bit, but the mirror starts to oscillate very heavily. So that's even worse. But the interesting point is if we go to very high frequencies, then actually we are in a situation where the ground can shake quite a lot, and the mirror only moves a little bit. And you see suppression factors here of 10-to-3 or something like that. So we reduce the vibrations, the impact of the vibrations on the mirror by a factor of 1,000. Now, if we manage to shift the resonance frequency to lower values, then the suppression at a given high frequency becomes even better. The problem is that to shift the frequencies to lower values, we have to make the pendula longer, which has technical limitations. Now, but what we can do, this is the same picture that you've shown before, what we can do to make the suppression even better, in the end, we need something like 10, 12, 14 orders of magnitude, is we can cascade it. So now this red sphere is no longer the mirror, it's just a dummy, and the mirror is now hanging on a second pendulum from the dummy. So the vibration of the dummy is suppressed already by a factor of 1,000, and then we suppress it to the mirror by another factor of 1,000, which means that the curve becomes even steeper, and even higher suppression factors can be realized, and we can go by several stages. So here are images of, this is now from the LIGO detector in the US. On the left side, you see the schematic drawing, how it's done. So it's supported on the ceiling, and from the ceiling, you have these two thin strings from which a metal platform is hanging. And then on this metal platform, there's another 2 strings here that support another metal platform. That's the second stage. Then there are strings here that support a glass object, which already looks pretty much like the mirror. And then in the 4th stage, there are 2 strings going down to the final object, which is the mirror. You can see an image on the right. You see at the bottom, that's the mirror. This is this mirror-shaped glass object. The first platform is up here. The second one is just visible there. And then there is the fixture on the top. And these objects are all hanging from very thin strings. The structure that you see around it is just a protection in case one of these strings breaks and the mirror, so that the mirror doesn't fall to the ground. There is no connection between the structure around it and the objects themselves. They're freely hanging in this suspension. And with such a suspension, these are 4 stages. For the Einstein Telescope, we will need 7. We can suppress the vibrations or isolate the mirrors from the vibrations around them. Now, I think I wanted to show you something about thermal, but I think I just skipped that, sorry, because we're running a bit out of time. And I come to an overview how the project would look like. So what you have to imagine is that we go underground, because underground all those vibrations are already much lower than on the surface. We have selected geologically quiet and stable region. So we have made, there was a study done all over Europe where we investigated different sites, and we in the end came up with a few that are quiet enough to build the Einstein Telescope. And the EMR is one of them. We have now these Michelson interferometers, but instead of using 90 degrees, we use 60 degrees, and we combine 3 of those Michelson interferometers together. So in each corner of the triangle, there is 1 detector located, 1 laser, 1 beam splitter, 1 photodiode. And the reason why we do that is that such a Michelson interferometer can detect gravitational waves only from certain directions. There are some directions where a single interferometer would be blind, and with a combination of the 3, we manage to detect gravitational waves from all directions. There is actually not just a single Michelson interferometer in each corner, there are 2. And the reason is that we wanted to span a rather large frequency range, and the higher frequencies, kilohertz frequencies, we need a Michelson interferometer with a rather high laser power to reduce quantum effects, while at the lower frequencies, 10 to 100 hertz, the thermal motion of the atoms on the mirrors is a problem, and we need to cool the mirrors. But with megawatt laser beams, it's impossible to cool the mirrors. So the low frequency interferometer has less power, but therefore is cooled and therefore has less thermal noise. And you can see the length of the arms. So these are the rulers. They're now 10 kilometers long. The Virgo detector that I've shown to you has 3 kilometer long arms. The LIGO detector in the US has 4 kilometer arms, and we want to build 10 kilometer arms. So that's the overview of the project, and thank you for your attention.
That we come to our first presentation of projects where you can start your own innovation project. The first presentation is about COMET. It's held by Dr. Matthias Grosch and Svea Binder.
Yes, thank you, Henrik, for the introduction. In the ET world, we love our acronyms. So COMET is co-making the Einstein Telescope, a project in the Interreg Germany, Deutschland-Netherlands region, where we support some of the developments that you have seen are necessary for these instruments. So let me quickly give you an overview just about the project, and then we do a bit more on the technology. It's one of those share information, connect people and stakeholders and network projects. So we want to bring together all kinds of companies from the German and the Dutch side of the border, share some knowledge. We also include knowledge institutions because you have seen it's quite a challenging technology. So we think even the more fundamental science side needs to be get into the project. We do introduction and connection of companies. We will have some networking events, several formats of workshops and webinars like today. This is more a starting point. There's more to come, so to say. And overall, we want to develop and set up 12 innovation projects. That is so to say the limit by the funding. If you have more ideas, we are happy to ask for more. And we want to transfer knowledge about the ET technology. So what you have heard today, what was given by Professor Achim Stahl, is a first glimpse that there are some developments necessary and some ideas and technologies in development. And what we want to share is that it's the side of the research institutes, the fundamental science and the ideas, what could be done, what could be achieved. And what we then want to accomplish with you together as companies is to bring the ideas and the technology into an industrial application. We have some focus on certain technologies. The ET needs a lot of different technologies, has a big scope, but we picked some that we think are currently in need of further development, that we also see that there's a lot of technology transfer potential that it can be used for the ET and beyond, so to say. You have seen we play around with lasers. We have a Michelson interferometer, so optics is of high relevance. It's the interferometer you've seen in the talk before is the basic setup, so to say. There's a lot of auxiliary optics and additional parts and components that, for the simplicity of explaining the principle, have not been shown. But be aware there's a lot of more optics components needed, so there's a lot of room for such developments. Vacuum and cryogenics. So you have seen the Virgo, which is currently running at room temperature. For the ET, we want to cool down. So it sounds easier than it actually is. Cooling down is not just turn on the fridge or something. We want to avoid any kind of vibration. And yeah, if you think about the fridge, you always hear this small buzzing of a motor engine running. So that's vibration. That's not how we can cool down. We have a bit of a challenge there. The whole thing is in ultra high vacuum, 10 kilometer long. This gives you a bit of a challenge how to achieve this, also economically feasible. So there we are open for project and ideas, how to improve the vacuum quality, how to make that run longer, easier, with low maintenance, because it's a huge infrastructure and it's underground. So you cannot just say, hey, go downstairs and fix it. It requires a very robust and long living system. Yeah, and also active noise mitigation. So we want to rule out quantum noises. This is a very specific one, but we also see their application for the upcoming quantum technologies. So something we would like to work on with you. Laser interferometry. I think that's a very obvious one, but maybe to quickly say that there are a lot of interferometers that are also used in various industrial applications. So there's a high relevance. It's not just this one interferometer, but being able to produce fine interferometers has a lot of application potential. And I think advanced data processing doesn't need much explanation. It is related to AI technology, to machine learning, to IoT. That's, I think, a no-brainer. A quick look how you can join. So if you are not yet, or maybe this is the first time you hear about the ET, we have a big mapping. We have a very vivid ecosystem. There is a lot of stakeholders, a lot of companies, a lot of institutes, also network agencies like us, working on the matter of ET together, so that we together do some development for it and bring it in the region. As you heard before, it's not yet fixed where the final location will be. We would like to have it here, and to boost the application for the location, we have a ecosystem mapping. So feel free to register there, show your competencies, make yourself visible. Join the mapping. Is totally free. It's just an offer to really show that you're interested, that you're a high-tech company. And then COMET offers some funding for the R&D that you do. So we don't just want to ask you, hey, develop something for us, but we say develop something with us. And we know development takes some money. So now my colleague Svea Binder will present you what kind of funding you can get by COMET.
Yeah, thank you, Matthias. So as Matthias already mentioned, for possible funding, it is necessary to come up with a consortium of a German and the Dutch SME or a knowledge institute. So we can also pair SMEs or SMEs with knowledge institutes to have a German-Dutch cooperation. If you apply for funding, we fund up to 75,000 euros, and the maximum subsidy rate is 50%. For the personal costs, we have hourly rates. These are the ones from the subsidy conditions of the COMET project. You can find the link to the documents down below. And non-personal costs must be included in the overhead of 30%. So if you have material costs or travel costs, they we in the overhead of the 30% of the personal costs. We have an example down below. So if the partner A have personal costs in the function group 2 and function group 3, it has a total personal cost of around 55,300 euros. And if partner B has only personal cost in function group 3, it has lower personal costs from around nearly 50,000 euros. And if we calculate the overhead of 30% of the personal costs and sum it up to a total, partner A has a total cost of around 77,000 and partner B around of 70,000, and the subsidy will be then half of the eligible costs. So far for the subsidy. Matthias, can you?
Yes, sorry.
Yeah. Yeah. So for this project, we already have, we have 3 calls this year. The first one is open now, and the deadline will be soon on the 10th April. We already have some matchmaking requests of Dutch companies. So if you're interested in applying with your own project idea, you can reach out to us. Or if you're interested as a German company or knowledge institute for matchmaking, you can also reach out to us as the call is open. But we support also during the calls in the application process or in creating a project idea. So far for that. And and these are all the project partners in the COMET project. And if you have an idea or questions, you can always reach out to one of us. We are located in different areas. So if we are close to your location, don't hesitate to reach out to us.
Exactly. And a quick one, since this is a publicly funded project, we want to thank our financiers that enable us to do COMET. And we're happy to, in the Q&A, or if you have registered and ticked the box of I would like to get in contact, we will be reaching out to you. Thank you for your attention.
Thank you.
Yes. So Ralf, the stage is yours.
Yeah, thank you very much, Hendrik, for giving me the opportunity to show a little bit the complementary funding opportunities which we have for our tri-national area here in Euregio Meuse-Rhine, Belgium, Netherlands, and Germany. I may say that we already had a similar project like COMET in the years 2021 to 2023. It was called ET-EMR, very similar conditions like they were presented already before. Now we have a new funding initiative which is called STIPP, and also the abbreviation is shown here. It stands for SME Transition Innovation Partner Projects. This describes very well what it is about. If you show the next slide, you will see that
that STIPP is regarding the scope a little bit broader than we had it in the COMET case. We have three different pillars. We are talking about industrial transition, green transformation, and also the health and aging society topic. But Einstein Telescope is one of the main topics we are interested, especially in industrial transition. So still a good opportunity to receive funding in these topics. The next one. So what do we fund? Who can benefit? Our target group is mainly the field of technology-oriented companies, especially SMEs and scale-ups. We are funding, similar to COMET, not single companies, but corporations, co-creations between companies. And if you look at large companies and research institutions, they can join as associated partners or subcontractors. So our focus is really on looking how can we support SMEs. Next one. In STIPP, well, our funding initiative is already running since mid-2024. We have the opportunity to provide ERDF grants up to 10 million euro. The same kind of financing as it was described before, 50% funding, 50% own means or own contributions. And what we also would like to implement is that we not are focusing only on the innovation projects, but we also want to implement an aftercare process and look also what is beyond the runtime of the innovation activities in order to see how can we help companies, how can we help SMEs further, how can we probably provide also innovation loans for the topic of further market entry. Our funding is a little bit depending on the number of companies and the number of regions. Here we have in total 5 different innovation regions here in Euregion Meuse-Rhine. And if a cross-border project is set up with 2 regions and 2 partners, it means that there is a maximum funding of 75,000 euro per company. So meaning that with 2 regions, you have 150,000 euro funding, 150,000 own contribution. And it, as you see here from the different pillars, it can go up depending on the number of regions. So if you have, for example, 4 regions, it is possible that each company in such a consortia can receive up to 125,000 euro. And meaning that the whole project can have a size of 1 million euro budget. So that's in a nutshell the funding volumes and the conditions. Next one. Here you can see our area to show you a little bit what we are talking about. So we have 5 different regions. And we also have an opportunity to involve also companies from the surrounding areas, but only to a maximum of 10% of the total project amount, grant amount. Well, one of the main topics that we are dealing with is, of course, the question, how do we find the right partners across borders? We do it with an idea sketch. That means that each idea provider should fill us in a meaningful, precise description of his or her project idea, and especially the required partner competencies. And then we provide these idea sketches and partner searches to our partners. If we are in Germany, we have a German idea to the Dutch and to the Belgian partners. And you see here in green that it is not necessary to bring with you your own partner. We are helping you from the side of the RDAs in finding the right partners. How does the process work? I already mentioned it. We have a short outline of the project idea. It should clearly describe the degree of innovation, and especially what do you need in terms of partners, what should be the partner profile. And then we arrange partner online meetings, meet and greet meetings, and the project idea provider in the end is able to select the most suitable partner or the most suitable partners. All project applications that we receive are assessed by a tri-national jury, an expert committee, and these are the criteria which will be taken into account. Just an overview here. And I already mentioned we have a runtime of around about 2 years now, so that I can already show you also some very interesting results of projects we have already achieved. So you see the projects from Core 1, we had mainly bilateral or only bilateral collaborations, and looking now at Core 2, we already had also trilateral cooperations and multilateral partnerships that were set up. You can see a little bit the topics, in industrial transition, green transformation, and health. You see the different budgets. And on the left side in the corner, you can see how it is divided so far after 2 calls over the different regions that are involved in the Eurasia-Rhine. We have in total 31 companies that are already working with that. Further on, how does the process work? If you have your partnership, if you have your consortium, you have to apply. The project application will be assessed, as I mentioned, and in the end, our board of directors gives a green light if the project is okay, if everything is fulfilled, and then you have opportunity within 24 months to carry out your project. We are looking at the different calls. We are very close to the next deadline, so that may be a little bit too ambitious if you are thinking on applying within STIPP. It will already close within 1 week. We have 3 million euro available, and if you are interested, you can find here also the link where you can get more information. Maybe more interesting, the next slide. For those who are newly involved, our next call is already planned starting in summer, from August 1st onwards to October 15th. We will have again 2.5 million ERDF funding available, and the further details will follow also soon when or after call 3 is now settled. Well, what is also important, the whole funding initiative is a multi-annual funding scheme, so it will run until the end of 2029, meaning that the last innovation projects can start in 2027. Normal for Interact, the expenditure reimbursement principle, companies receive the funding after the implementation of the different steps. And it is possible, maybe interesting, especially for small companies, that up to 30% of the total funding amount can be received by the SMEs or by the smaller companies also as an advance payment. If you are interested, if you have questions, you can see here the 2 contact points in North Rhine-Westphalia. On the one hand, NMWP management. They are also, as you heard, active in the COMET project. And we, Agit here from Aachen, we are the ones in North Rhine-Westphalia who can answer your questions. And maybe the last slide, so that you also can see an overview, which are the partners. You can see our partners starting from Leof in the Netherlands, POM Limburg in Belgian Limburg, and also Vlaio in Flanders. And for the French-speaking part of your region, Meuse-Rhine, and German-speaking community in Belgium, it is Wallonie Entreprendre, and you can also see our finances here. Thank you very much.
Yes, thank you. See, because now we have our last presentation. It's something like a best practice. It's Lucid. It's a project which already started in STIPP, and I would like to hand over to Dan.
Thank you for the opportunity to speak and to show one of the applications within the STIPP program. So we are the Lucid consortium. I myself am Dan Vlekke from the company and lead partner Netalux. And today I'll show you a bit of what we have done already with STIPP and what the project is about. So indeed, again, with the Einstein Telescope, what Lucid will do is we will have our application in the beam pipes. So the 10 kilometers of beam pipes per leg of the triangle will need to be made in an industrial environment. And there's a lot of debris and dirt that can come onto the material of those beam pipes. Now, traditional methods, they are very water and energy intensive to clean them. So to get rid of all the hydrocarbons that can occlude the laser beam when the vacuum is made. So therefore, Lucid, the Lucid project also is, of course, an abbreviation of laser cleaning the ultra-high vacuum pipes for the Einstein Telescope. So we are a cross-border consortium consisting of a Flanders company being ourselves Netalux, a Walloon company Silex, then from the Netherlands we have SAC, and from the Aachen region we have Isatec Aachen. What we are creating is a smart and autonomous laser cleaning system that can achieve microscope level cleanliness with only the power of light by using lasers. So indeed, a more green way of cleaning the beam pipes. Let's see, is it going through? Yeah. So our innovation project partners, as said, Netalux ourselves, we will be delivering the advanced laser cleaning system and the cleaning strategies. And we also are the project management, so the lead partner with project management. Isatec from Aachen will design and dimension the waste extraction system. So the laser will get rid of the contamination on the metal of the beam pipes on the inside, or the inside surface. And that waste needs to be extracted to be sure that it's not redepositioning on the material. SAC from the Netherlands, they will provide the cleanliness control software. They will do sensor selection and the cleanliness validation intelligence. So to make sure that everything that we clean is actually cleaned and no more redepositioning or hydrocarbons are left after we have a cleaning passage, that will be the responsibility of SAC to make sure that we have that quality control. And then Silex from the Liège area, they will do the industrialization and the seamless deployment in production environments. So they will provide a robotic system on which all the three systems from the other partners will be integrated, and that can then crawl through the finished production pipe, or in another production process can it then be implemented via their industrialization processes. Then, so we're also here to talk about us the four partners being the SMEs and then the STIPP organization. We as lead partner, we came in contact with STIPP and just for ourselves, Flyo, with Luc Deprognou, also here in the meeting, to do a partner search. So we had an idea of cleaning the inner tubes, and they helped us to set up a partner search where we quickly found the three partners. Actually, I think in a month's time, we were able to set up the consortium and start with drafting the application. The application also then got a lot of guidance by Flyo, Agit, and then Walloon Entreprendre also, and I think then also Liof. So every partner got their advice from the supporting agencies. Then also in my own opinion and experience, a fast and open communication about everything that needed to happen. So you could call them and they would immediately make their commitments to providing a solution for your problems. So that was a big plus for me. And then the vast network of innovators and institutes. So we from Lucet already got the chance to talk on a large networking expo, so Space Expo in, I think it was Bremen, where we got to talk with POM Limburg and the people of the Einstein Telescope. And then, of course, I think that's one of the most important things, the funding. So they also helped, so STIPP is providing funding, but they also helped in setting up the proper funding structure and what we need to do to get it, to start innovating. So that's my experience with STIPP, and I would say it's a very nice experience already. That's it for my short presentation on the Lucet project, and I want to thank you for your attention.
And now we have time for questions. I think it's, thank you for the presentation again. And I think it's very interesting, Achim Stahl. Every presentation I learn something new. So, but it's still high tech. So, but again, if you have questions, I think there were first questions in the chat, but they were already answered as far as I know. If someone has a question, he or she can raise the hand and unmute themselves one after another. So go ahead. What are your questions? What do you want to know about technologies, about funding? Do we have questions? Erwin Hofstede, please.
Yes, thank you very much. Is it correct that STIPP is only for the South Dutch people from Limburg, or is it wider abroad? The map was a bit difficult to read during the presentation, and it looks like it's only Limburg. Is that correct?
Yeah, maybe I can directly answer it. It is, of course, the program area of Euregio Meuse-Rhine, meaning that South Limburg and to a certain part also Middle Limburg is involved. Yes.
Okay, so Brabant is not in the area. Okay.
Right. Brabant would be a functional area, so that currently it is only possible to receive a maximum funding up to 10%. We have some discussions with the program in order to see if we can hire this a little bit. But of course, the main target is to focus the cooperation and the funding on this tri-national region.
Okay, thank you very much.
Maybe it could be, depends on where in Brabant, that it is covered by the COMET project.
Yeah, true. I'm aware of COMET, and I'm also already in discussion with people from COMET. But I didn't know about STIPP before, so I was really curious if I had read the map all right, and it seems to be. So thank you very much.
While we are waiting for further questions, I would have a technical question. Mr. Stahl, you said that you will, to provide these vibrations, you have two mirrors, this dummy mirror and the correct mirror, and they are connected with thin strings, you said. What is the weight of these mirrors? Thin strings? Sounds a bit heavy.
So in the current detectors, the mirrors are 40 kilograms. For ET, we want to go to 200 kilograms. The reason is the heavier the mirrors, the less they shake. Now, the new mirrors will be made from glass for one interferometer, silicon for the other, and the strings should have the same material. So these will be glass strings and silicon strings, and they're actually, we call them strings, but if you actually look at them, they're more like thin rods. So the silicon strings are about 3 millimeters thick.
Interesting. Thank you very much. I
Working
think there's
at the moment on how to bond the strings to the mirror material. That's one of the technologies which is currently in the focus of what we are doing.
Yeah, I think simple glue might not fit. Yeah, it's all high tech. Yeah, thank you very much. I think there's another question in the chat. So it's in German. Wer definiert denn die Kriterien, die für ein Projekt relevant sind und die mit Partnern durchgeführt werden sollen? Was muss oder sollte erforscht werden, um ein Projekt zu realisieren? Die haben wir noch nicht beantwortet, glaube ich.
Ja, da kann ich gerne was zu sagen. Auch wenn gewünscht Deutsch, wobei ich würde für die internationalen Gäste. So in English, maybe quickly. The question is, which criteria, how are they defined, and what is relevant and necessary to do a project? So while the ET is very dedicated and very specific technology, which we know and understand, the criteria are an international consortium, so cross-border one, since we are in interregional projects. We want to have a solid technical foundation explained by the consortium. So you should have an idea which technology you're going to advance. But this advancement does not have to be that you apply with a final solution or a way to final solution for the Einstein Telescope. So it's more of you make a first step in development. You do not have to necessarily develop the final part that is becoming a building thing in the ET. So you should make a step forward, and the direction should be towards the ET, the Einstein Telescope. Yeah, and then it should be a reasonable advancement for the proposed costs. Yeah, but it should also, this is one of the criteria, you should also develop something that has a benefit for your company, that is going towards a product or an application that you economically want to develop and reach. So it's not a fundamental science funding, it's not a just your own product funding, but we want to have, it would be great if you have the synergy of developing something that is of help for your future product and application, and that is of help for the ET. For details, please reach out. We can discuss it a little more and check if the technology is a match. Thank you.
Okay, do we have one last question? Oh, two. So I think, Jürgen Martin, you were the first one.
Yes, I have a technical question. Perhaps Mr. Stahl can help me on that way. We are building measurement solutions, and we have the capability with our systems that we can split high frequency and low frequency signals at the same time. So what we are detecting with the Einstein Telescope are low frequency effects. But does it make sense to record and analyze all three recording data to get an exactly phase shift in between the three detectors, so that it might be possible to have a triangulation possibility?
Okay, so in your terminology, what we are doing is probably all low frequency. So the frequency range we want to start at 2 to 3 hertz, and at the upper end there is no clear cutoff, but so typically say 40 kilohertz is so the sensitivity slowly fades, but in the 10th of kilohertz range. Phase shifts between the detectors are relevant if we don't go for a triangle. This is an option to build, instead of a triangle, 2 L-shaped detectors, but then you would separate the 2 Ls by 1,000 kilometers. And then the phase shift is very relevant to localize the origin of the source. If the 3 detectors are at the same site, the sensitivity in the phase shift is not good enough to see any resolution on the direction. The direction is mainly determined in the triangle by the fact that the sensitivity of each detector is direction dependent. So you will see different strengths of the signal in the 3 detectors depending on the direction from which the signal comes. And this will be the main information to get the sky localization, as we call it.
Okay, understood. So resolution for phase shift detection of nanoseconds, or perhaps going into picosecond range, is not enough for triangulation. So we need to do a synchronization between different installations. So that might be more efficient.
Yeah. Yes. So and there is so we assume that also on top of the Einstein Telescope there will probably be a similar project in the US. It has the name Cosmic Explorer, and then the baseline is more like 10,000 kilometers, and this together will allow us to do triangulation or trilateration, as it actually should strictly be called. Also, we always also say triangulation.
Okay, thank you.
Okay, and there was another question in the chat about the temperature needed. It's already answered in the chat. So the temperatures needed for the mirrors shall be controlled about 10 to 20 K. And there's another person with a raised hand, Antoine Wu.
Yeah, thank you very much.
Yeah.
I also have a short question to Professor Stahn. I'm working in Fraunhofer IPT in Aachen, Germany, in the group of precision optic manufacturing. And in the last few minutes, you mentioned that you have a demand on how to bond the glass to string. Because at Fraunhofer IPT, we are working on, or our group is working on the glass to different substrates material bonding. Could you please explain a little bit what is the main challenge that you are looking or searching for an innovation or solution?
Actually, we're more working on the silicon, on the low frequency part. So in Maastricht, there is a prototype set up of the low frequency of the cooled interferometers. And there we're currently trying to bond the wires to the silicon mirrors. And this is difficult to create the necessary strength. I know other groups are working on the glass mirrors, but I don't know the details on the glass bonding. I'm sorry. If you're interested, send me an email. I'm trying to dig out which groups are actually working on the glass mirrors. I don't know by heart right now.
Okay, thank you very much. I will do it. But could you please just give a very short quantitative, what is the bonding strength that you are looking for?
Well, you have an area of, we can design, but a square centimeter, maybe 2 if you want, times 2. So there are 2 strings, one on each side. And this has to carry 200 kilograms.
Okay, I see. Yeah, very promising. Thank you.
Okay, thank you very much again. So I think now we are running out of time. But if you have further questions, we will send the presentations, we will send the screen recording and the contact points. So if you have further questions, you will get enough possibility to get into contact with the right persons. From my side, thank you very much for your time and hope we will get a lot of interesting projects from you. Thank you very much.
Bye-bye.